Here we have a particle of mass m, and we have it moving to the right at speed v naught, and we imagine a particle that is somewhere down here, same mass and same speed, such that they collide here and they move together like that. So they have some final speed like that, right? So we're basically applying a kind of pull, except that the objects stick together and there's some angle there. We want to know what this is and what that is. And so because there are no external forces, the forces are only between the particles here, momentum conservation applies. So we have the P initial equals P final. And so we have X and Y horizontal and vertical, if you will, components. But we are on a horizontal surface, let's say, so that the normal force, the gravitational force on each object is balanced by the normal force. So the sum of the forces is 0. This applies, and the X component or horizontal component reads m v naught initially, right? Because this is all in the other direction. So afterwards we have 2m v final, but it's the part along here that matters, so it's cosine of theta. That's the X component of the momentum. And the Y component also has the same magnitude, and the difference here is 2m v final sine theta, right? We can see that both of these have to be the same, so there's only one angle that allows this to be possible. If I divide this equation by this equation, we see that we get the tangent of theta, and that's equal to 1, so theta is the inverse tangent of 1, and we could argue from first principles, the sine and the cosine. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and they have to be the same, so these two sides have to be the same, and therefore the angle has to be 45 degrees, or pi over 4. So we know the angle, and now we can use any of these equations to find v final as v naught over 2 cosine theta, or v naught over 2 cosine theta. They're the same, and that's v naught over 2 cosine of pi over 4.